Hello. So we will start today talking about matrix multiplication. So just yet another operation on matrices. Remember last time we talked about matrix addition and the scalar multiplication. For the matrix multiplication, normally we would take a quick time to go over this operation because it's just like any other operation. It's defined in a certain way, and we just learn it by looking at several examples. But as I mentioned before in this class, even for basic stuff like operation on matrices or many other introductory portions of the course, I really like to give justification for why some of these mathematical tools are invented. There are many reasons. Some of them are purely mathematical, but others are actually practical. So before we actually know how we multiply matrices, let's actually go over a real-life example that is conducive, as you'll see later, to defining this multiplication of matrices in the way we actually define it. So what I'm going to show you basically is just one possible use of the matrix multiplication. So let's suppose we have a fresh item store that wants to sell certain items, let's say 3 types of fruits. And then in a given day, there are certain quantities of different fruits available in the store. And for simplicity, I'm going to choose obviously smaller numbers than what you will normally find in a store. So let's suppose we're looking at 3 types of fruits, apples, let's say peaches, and grapes. And we want to list the quantity in the beginning of these items in a given day, let's say in pounds. So for example, let's say the store has 10 pounds of apples, 12 of peaches, and 15 pounds of grapes. So already you notice that data can be written in a matrix form. So far we just have only one row. We'll get to matrices later. And in this case, the data is the quantity. And let's say separated from the quantity, we have the price, unit price information in dollars per pound. So the unit price in the sense that the amount of dollars per pound for each product. Again, we have 3 types of items, and let's this time write this information by column. So the unit price, you will see later why we do that. So the unit price for apples, let's say, is $2. The unit price for peaches, let's say, is $4. Again, forget about the realism of this. I don't know if that's realistic to have, twice as much for the peaches. And then the grapes, let's say it's $3. Again, these are unit prices, so this is per pound of product. So a natural question then is to ask if the store manages to sell this. So let's say actually when I write here quantity, let's say I meant the sold quantity on that day. Then the natural question is to ask what is the revenue by selling these items. And obviously you're going to have to multiply the quantity by the unit price and add together, right? So you sold 10 pounds of apples at $2 one per pound. So you multiply 10 by 2, to which you add the revenue for the peaches, 12 pounds, and then multiply that by the unit price. And then finally the grapes, 15 multiplied by the unit price. That'll give me 20, plus 48 plus 45. What is it? That's 68 plus 45. That's $113. Okay, so what you just saw basically was an example of what we're going to call the multiplication between a row matrix, so a matrix made by a single row over here, and a column matrix, which is given by this column of the unit prices. So this is also called in linear algebra dot product actually. And again, the fact that one of them is given by row and the other by column will make sense a little bit later when we actually define multiplication of matrices. But for now, what matters here is that the number of components for the row and the columns are the same. So when we talk about the multiplication between a row matrix and the column matrix, one condition is that they need to have the same number of components. So they need to have the same number of components. Otherwise, the multiplication is not defined. So it's important to understand from the beginning that multiplication of matrices is not defined for any pair of matrices. There are conditions in terms of rows and columns. So in this case, if you have a row and a column, they need to have the same number of components. So let's take an example, another numerical example. Let's say you need to multiply the row given by -1, 2, 3, and 4, multiplied by the column, let's say 2, 0, 1, and 3. There are the same components, 4 components for each. So therefore the dot product, or the row times the column, in the way we define it so far, it's -1 times 2, plus 2 times 0, plus 3 times 1, plus 4 times 3. Feel free to go faster once you understand how you do this later. Right now I just write it like that so you know how you pair each entry, right? So component by component and add the products together. So this is going to be -2 plus 0 plus 3 plus 12. 12 plus 1, that's 13. So how does that lead to a more general definition of matrix multiplication? Well, let's actually go back to our original story with the farmer. And let's suppose things change from one day to another. Let's say this is day one situation for both the price, for both the quantity and the price. But let's say on a different day, and I'm gonna, let's see, well, let's write it again here. So on day one, on the quantity matrix, let's copy again the quantity, it's 10, 12, 15. But let's say on day two, we have a different set of, a different quantity sold, right? So let's say in the second day, we have 5 apples sold, 5 pounds of apples sold, 3 pounds of peaches, and 20 grapes, 20 pounds of grapes. Again, these are apples, peaches, and grapes in pounds. And then on the second day, we have, let's say, different. We decide to change the price, right? So on day one, when we look at the price matrix, so again, for apples, peaches, and grapes. So again, on day one, we had $2, $4, and $3. But then on the second day, you decide to change the price and then set it for, let's say, $3 the apples, $2 the peaches, and then let's see, 3, 4, let's say 4, let's say $4 for the grapes. 3, 2, 4. So now notice that there are many combinations you can make, right? So you can have actually, so it doesn't have to be actually by the day. Basically, you can have any combination with any unit price you have, right? So let's say in one day you may have this quantity, and then in a different scenario, or on a second day you have this, and you want to basically save in a separate matrix the revenue in various scenarios. So what if you sell, let's say, this quantity in day one with this unit price given by this column? What about you want to choose a different unit price given by 3, 2, 4? So if you look carefully, you have actually 4 possibilities. You can pair the quantity 10, 12, 15 with the two sets of unit prices over here. Or you can combine the second possibility of the quantity, 5, 3, 20, again, each with the unit prices given there. So let's write again the first one we computed, right? So I mean 10, 12, 15 with the unit prices 2, 4, 3. So you had 10 times 2 plus 12 times 4 plus 15 times 3. You gotta make sure you pair them correctly, right? I mean apples with apples, peaches with peaches, and grapes with grapes. So we did that already above. That was $113. But let's say you use the same quantity, but with the unit prices 3, 2, 4. So 10 times 3, and then plus 12 times 2, plus 15 times 4. And that'll give me 114. You can check with your calculator if you don't want to spend too much time on this. So that's 30 plus 24 plus 60. Then again, going back to the original quantity, excuse me, the second quantity, 5, 3, 20, with the first set of price. So I can have 5 pounds times $2. So 5 times $2, 5 pounds times $2, then plus 3 times 4 plus 20 times 3. So let's see, that's 10 plus 12 plus 60, which gives me $82. And then the last combination, I can have again the same quantity, 5, 3, 20 paired with 3, 2, 4. So 5 times 3 plus 3 times 2 plus 20 times 4. That's 15 plus 6 plus 80. That's 21 plus 80. That's $101. So if you view what I just showed you in terms of matrices, this is an example of matrix multiplication. So one matrix denoted the quantity in this justification, basically, that we, in this meaning of the entries that you have here. And the second matrix by column contained unit prices. Okay, we're going to define formally the matrix multiplication pretty soon. But what I want to point out is that all these combinations with rows and columns in this interpretation will give you the matrix, the product matrix, which in this case is nothing but the revenue matrix, if you want. So the first row with the first column, you can write it in the first entry here in the answer, 113. The first row with the second column was 114. And then the second row with the first column was 82. And then finally 101. So that is the revenue matrix. So with matrices, you can basically combine lots of different sets of data points. So each row in the first matrix can mean any possible set of quantities sold. And you can go as deep as you want. You can have 3, 4, 5, how many entries you need or you have in terms of the quantity sold. And then the columns can also be extended. They don't have to be just 2 of them. Because you can have lots of different set of data points for the unit price. The only requirement, if you're careful, is that the number of products should be in agreement to the number of unit prices. So right away, you realize that if this is a matrix multiplication, we can't multiply any matrix with any other matrix. The number of, and we're going to write that on the second page, but the number of columns in the first matrix should coincide with the number of rows in the matrix you multiplied it with. Because you basically do a row times a column in the way we defined it above, and you need to have the same number of components when you do row times the column. So this is basically one possible motivation for the matrix multiplication. On the second page, we're going to move on to write formally the definitions of these operations, and then we will finish with some examples as usual. Okay. All right, so let's take a moment to write the definition, like I said, in a more formal way. How do we multiply a row and a column matrix, also called the dot product? So basically, if you have a row and a column with n components or n entries. So for example, let's say you have, so let's the n entries, the product is defined in the following way, right? So suppose the first column, the row is given by the entries x1, x2, xn. And then usually the dot product, to not be confused with the regular multiplication, it's with a dot a little bit more emphasized like that. And then let's say the entries in the columns are y1, y2, yn. So basically this is pair component-wise multiplication and addition. x1 times y1 plus x2 times y2 xn times yn. So as let's take another quick example. Let's say you have minus 2, 3 dot column matrix 6, 1. So that's minus 2 times 6 plus 3 times 1, which gives me minus 12 plus 3, and that's minus 9. We always arrange it in the row times column because that's conducive to the matrix multiplication later. Because normally in linear algebra, the dot product just requires two matrices. Doesn't matter if they're column or rows. They don't have different meaning if you just handle rows or column matrices basically. So the dot, well, there's also the concept of vectors in linear algebra, but we don't get into that right now. So for now, we define the row and column multiplication in this way. So based on that, once we know how to compute the row times the column in this way, let's define again formally the matrix multiplication. And here, suppose we have a matrix A, and remember how we describe the generic term of a matrix, let's say given by Aij, with m rows, n columns, and a matrix B described by Bij with, pay attention here, n rows and p columns. So the number of columns on the matrix A must coincide with the number of rows on the second matrix that you multiplied it with. So basically for A times B to make sense, A must be m by n, that is n columns, and doesn't matter the number of rows. And B must be n by p, n rows, and then it doesn't matter the number of rows for B. It's just that the columns of A must be in agreement with the columns of, the columns of A must be in agreement with the number of rows for matrix B. So these two matrices, if they are in that configuration, then A times B, the product, is a matrix C given by the generic element Cij, where Cij is obtained by multiplying row I of A with column J of B. So each element is basically coming from a row of A multiplied by a column of B. And before we go over several examples, an important remark: the matrix C, which is again A times B, will have m rows and P columns. So it will have the number of rows of A and the number of columns of B. You will see that automatically if you do the product correctly. I mean, it's going to come basically natural that you'll have the same number of rows and columns as A and B, basically. So let's actually write a couple of examples. So suppose that matrix A is given by 1 minus 2, 3, 4, 0, 6. And then matrix B is given by 0 minus 2, 1, 0, 2 minus 4. So notice this guy, A has 2 rows, 3 columns. B has 3 rows, 2 columns. Okay, the number of columns of A coincides with the number of rows of B. We can proceed and find the product. So 1 minus 2, 3, 4, 0, 6 multiplied by 0 minus 2, 1, 0, 2 minus 4. And again, in the beginning, we're going to emphasize here how we come up with the product. Later on, you can go faster. So let's actually write 2 steps, okay? So in the for the first entry, you do row 1 times column 1. Row 1 in the first matrix, column 1 on the second matrix. Then you do row 1 times column 2. Then row 2 times column 1. And finally row 2 times column 2. In the sense of the dot product we mentioned, remember here, right, in the beginning of the page. Okay, so what does that mean in my particular example? So let's continue this example. Row 1, let's underline. Later on, I'm not going to underline them because I don't want to make a mess, but look at row 1, column 1. So that's going to be 1 times 0 plus minus 2 times 1 plus 3 times 2. You're done with the first entry of the product. Then we're going to do row 1 times column 2. So it's going to be 1 times minus 2 plus minus 2 times 0 plus 3 times minus 4. Moving on, row 2, column 1. We do 4 times 0 plus 0 times 1 plus 6 times 2. 4 times minus 2. Now we do row 2, column 2. 4 times minus 2 plus 0 times 0 plus 6 times minus 4. Remember to pause whenever needed to catch up. So what do we get? Let's see. 0 minus 2 plus 6, that makes it 4. Minus 2 minus 12, that's minus 14. And then 6 times 2 plus 0, right? 0 plus 0 plus 12, that's 12. And then minus 8 minus 24, that makes it minus 32. Again, pay close attention. We multiplied a 2 by 3 matrix with a 3 by 2 matrix, right? So we managed to do this because the number of columns on the first coincided with the number of rows on the second, and the answer was 2 by 2, right? So a matrix given by 2 rows and 2 columns. So I hope that's clear. Another important piece of, another remark that I want to make here is that the multiplication, unlike real numbers, is not commutative. If you change the order of multiplication, you normally don't get the same answer. So in general, A times B is not equal to B times A. So actually, if you don't have the same number of rows and columns, you will never have an equality because the type of matrix will be different if you switch the order of multiplication. And I'm going to show you this with this example as we move along with the next page. All right, so I wrote what the answer from the last page, A times B. let's see what happens if I switch the order of multiplication from B to A. So B times A. So if I start with B and then A. Okay, so notice now the first matrix has 3 rows, 2 columns. And then kind of messy here, so 2 columns. And then the second one has 2 rows and 3 columns. So again, I can do the product because the number of columns on the first matrix coincides with the number of rows on the second matrix. But notice the answer I'm going to anticipate already is going to be a 3 by 3 matrix, unlike a 2 by 2 matrix before. So for sure, B times A won't be the same matrix as A times B. So when you do the pairing, you're going to have row 1 times column 1, row 1 times column 2, right? So you have more combinations, row 1 times column 3, row 2 with C1, row 2 with C2, row 2 with C3, and finally row 3 with C1, C2, and C3 respectively. Okay, so same definition, but in this case you have more elements, although each will contain fewer basically multiplications. I don't think I can actually fit it here. Well, let's see. Sometimes I get greedy with the space and I pay the price, but let's see what happens. So row 1 times column 1, and by the way, you can actually pause and do it on your own and then check with me the answer later. So 0 times 1 plus minus 2 times 4. Yeah, that's not going to work. So let's actually do it here, so we have more space. So 0 times 1 plus minus 2 times 4. That's the first entry. Row 1, column 2, 0 times minus 2 plus minus 2 times 0. And then moving on, row 1, column 3, 0 times 3 plus minus 2 times 6. Now with row 2, 1 times 1, row 2, column 1, 0 times 4, 1 times minus 2, 0 times 0, 1, 3 plus 0, 6. Finally, the last row with column 1, 2, 3, 2 times 1 plus minus 4 times 4, 2 times minus 2 plus minus 4, 0, and then 2 times 3 plus minus 4 times 6. So from now on, actually, I'm going to do it a little bit faster, as many of these computations can be done mentally, right? So let's see. First entry will be minus 8, then 0, then minus 12, and then 1 plus 0, then minus 2, and then 3. 1 times 3 plus 0. 2 minus 16 makes it minus 14, then minus 4, and then minus 18. 6 minus 24. So that is B times A. All right, so the last remark I want to make, which will come handy later, it will be an important definition. There is something called identity matrix. A matrix that plays the role of 1 for square matrices. So this type of matrix is a square matrix. Let's actually define it. Is a square matrix with 1 on the main diagonal and 0 elsewhere. And usually it's denoted by I sub number the rows and columns. So for example, if you have an identity matrix of 2 rows and 2 columns, that's going to be 1, 0, 0, 1. So 1's on the main diagonal, 0's elsewhere. Identity matrix with 3 rows and 3 columns, that's going to be 1, 0, 0, 0, 1, 0, 0, 0, 1. I4, same idea. 1's on the main diagonal, but 0 elsewhere. Basically, like I said, this plays the role of 1 in the sense that if you have a matrix with n rows and n columns, A times In is equal to In times A is equal to A. So it plays the role of 1 in the sense that if you multiply any square matrix with the corresponding identity matrix, you always get the same matrix to begin with. Okay, so it's very easy to check. For example, let's say I multiply a matrix 2 by 2, let's say with entries A, B, C, D, times 1, 0, 0, 1. So if you follow carefully the way you learn how the matrix multiplication is defined, row 1, column 1, row 1, column 2, C times 1 plus D times 0, C times 0 plus D times 1. No matter what A, B, C, D are, you always get the same. Okay, so any 2 by 2 matrix times I2 will give you the same 2 by 2 matrix. So that is the identity matrix, which plays an important role later when we learn later the concept of the inverse of a matrix. So these are the matrix multiplications we're going to deal with, and we're going to make good use of them to figure out some other interesting uses of these operations later. So that's it for today. I'll see you next time.